Trends in electrode potential of dye-positive ions. Let's discuss with the help of graph. These are red shows observed values and green shows calculated values, and most of the cases they tally with each other. Here we find higher value for chromium and for iron. So this shows the difference between observed values and calculated values, and you will find except in two cases, in all other cases observed values and calculated values are exactly same. The unique behavior of copper having positive electrode potential shows its inability to liberate hydrogen from acid because it is less reactive than hydrogen. Only oxidizing agents, nitric acid and concentrated sulfuric acid react with copper, and acids are being reduced, forming sulfur dioxide in case of sulfuric acid and nitrogen dioxide in case of concentrated nitric acid, and nitrogen monoxide with dilute nitric acid. Whereas copper gets oxidized to copper oxide and reacts with nitric acid to form copper nitrate, sulfuric acid to form copper sulfate. The general trend towards less negative electrode potential values across the series is related to the general increase in the sum of first and second ionization enthalpy. It is interesting to note that the electrode potential value for manganese, nickel and zinc are more negative than the expected trend because their sublimation energies are comparatively less or enthalpy of atomizations are less. Thermochemical data in kilojoules per mole for first row transition elements. This is giving the thermodynamic data for enthalpy of atomization. This is the first ionization energy, second ionization energy, hydration energy, and electrode potential. The most important point here is the electrode potential is the resultant of enthalpy of atomization, ionization enthalpy, and hydration energy. And if we have higher hydration energy which can compensate ionization energy and enthalpy of atomization, we will have lowest value of reduction potential and the substance metal will be good reducing agent. For example, titanium +2. Vanadium has got -1.18 and -0.90 is for chromium. Manganese has -1.18. So you will find there is an irregular trend in the reduction potential of 3D transition series because there is irregular variation of enthalpy of atomization as well as ionization enthalpy. In general, hydration energy increases, but it decreases here, then it goes on increasing. Zinc has got lower. So hydration energy also has irregular trend. Except copper has got plus 0.34 volt. Others have negative reduction potential, and reason is that its ionization enthalpy is quite high, although enthalpy of atomization is not very high. The stability of half-filled d orbital in Mn+2 and completely filled d10 electronic configuration in Zn+2 are related to their electrode potential value, whereas electrode potential for nickel is related to highest negative hydration energy. In case of nickel, we find that hydration energy is quite high. And copper +2 is more stable because it has very high hydration energy. So with the help of these values, we can discuss the stability of oxidation state and their reduction potential. Let's take up trends in electrode potential of Mn+3 to Mn+2. The comparatively high value of manganese shows that Mn+3 readily changes to Mn+2 because of 3d5 more stable electronic configuration, whereas comparatively low value of Fe+3 to Fe+2 because Fe+3 is already stable with 3d5 half-filled p orbital. The comparatively low value of vanadium is related to stability of V+2, that is half-filled T2G orbitals like Cr+3, which also has half-filled T2G orbital. Trends in stability of higher oxidation state. The highest oxidation state is achieved in TiCl4, TiX4 tetrahalides, VF5, CrF6. +7 oxidation state of manganese is not represented in halides, rather in oxyhalogen compounds. And beyond manganese, no metal can form trihalides except FeCl3 or FeX3 and cobalt F3. The ability of fluorine to stabilize the highest oxidation state is due to higher lattice energy of the fluoride, as in case of COF3, or by a higher bond enthalpy in terms of higher covalent compounds VF5 and CrF6. All copper plus 2 halides are known except of iodide. Reason is that cupric ions get reduced with the help of iodide ion to form cuprous iodide plus iodine is liberated. It undergoes disproportionation reaction. Cu plus 1 is less stable. It changes to Cu plus 2 and copper is formed. That is, copper plus 1 is oxidized as well as reduced. That's why this reaction is called disproportionation reaction. The stability of copper plus 2 rather than copper plus 1, although electronic configuration point of view 3d10 it has, but still copper plus 2 is more stable because hydration energy of Cu plus 2 is quite high, which compensates second ionization energy. That's the reason copper plus 2 is more stable. The highest oxidation state in oxides coincide with the group number and is attained in scandium trioxide and manganese heptoxide. Beyond Group 7, no higher oxide of iron above Fe2O3 is known. Mn2O7 is a covalent compound because it forms multiple bonds and manganese cannot lose 7 electrons. It can share 7 electrons with oxygen atom and result in the formation of multiple bonds. The ability of oxygen to stabilize this highest oxidation state exceeds that of fluorine because oxygen is capable of forming multiple bonds whereas fluorine cannot. In covalent oxides Mn2O7, each manganese is tetrahedrally surrounded by oxygen atoms, including MnO-Mn bridge. The tetrahedral MON- ions are known for vanadium plus 5, chromium plus 6, manganese plus 5, manganese plus 6, and manganese plus 7.